Let's investigate the quantum order-finding subroutine of Shor's factoring algorithm. We will begin with an overview of the phase estimation procedure. Then we will see how to adapt phase estimation to solve the problem of order finding. Consider a unitary operator denoted by capital U. U has an eigenstate denoted by ket lambda sub s. And this eigenstate is associated with an eigenvalue, which we can express as e to the 2 pi I phi sub s. That's the same index s that we're using to specify which eigenstate we're dealing with. And then we can write the eigenstate ket lambda sub s over here. So the action of this unitary operator on the eigenstate is equivalent to multiplication by this eigenvalue. And the eigenvalue is specified by phi sub s. So given that we have some knowledge about how to apply u to its eigenstate, we can develop a procedure, which is called phase estimation, to estimate the value of phi sub s. That is the goal of the procedure depicted in this quantum circuit diagram. So let's have a look at the key stages in this procedure. So we're going to begin with step 1. Step 1 is initialization. We're going to initialize two registers. We have an m qubit register and an L qubit register. We can call this the top register and the bottom register, or we can call them register 1 and register 2. By convention, we're going to write this top register on the left and the bottom register on the right. That's when we're constructing expressions in Dirac notation. So we want to initialize the m qubit register in the state 0. And what do we mean by 0? Well, we have m qubits in total. So we want to initialize all of them in the computational basis state labeled by 0. So we can think of this as a string of m zeros. And we can write that more concisely as a single 0 over here. And what about this register? We're going to initialize this L qubit register in the eigenstate ket lambda sub s. So that is the eigenstate of the unitary operator we're dealing with. So this step is called initialization. We are initializing these two registers. And this number L over here, that is the number of qubits we need to define this eigenstate. And M, we have more freedom when we choose M. M depends on the level of precision we're looking for. So M can be chosen with L in mind. So we can consider what L is, and that's going to inform the decision. And we also need to consider the level of precision we're looking for. And that's going to tell us how many qubits we need in this top register. So step 1 is initialization. Step 2 is creating a superposition. So how do we create a superposition? Well, we're going to apply the Hadamard gate to all of the qubits in the m qubit register at the top. So that is what this is telling us. We have the Hadamard, and then there's this little tensor product symbol with m. So this is shorthand notation for applying a single Hadamard gate to all of the qubits in the top register. What is that going to produce? It's going to give us a superposition of all of the computational basis states for the top register of qubits. We can write that as a normalization coefficient of 2 to the minus m on 2. This m over here is the number of qubits we're dealing with. And then we're going to have the sum over some index k going from 0 up to 2 to the power of m minus 1. So why is there a 2 to the power of m? Well, we're looking at a dimension of a Hilbert space. So that is the dimension of the Hilbert space for this top register. If we have m qubits, then the dimension of the Hilbert space is 2 to the m. Since we are starting from 0, we have to subtract 1 from this end value over here. And that's going to give us all of the values which specify the individual computational basis states. And then we have the ket labeled by k, and then finally the ket labeled by lambda sub s. So this is the result of all of these Hadamard gates applied to the qubits in the m qubit register at the top of this quantum circuit diagram. Now that we have a superposition, we can go to the next step, which is step 3. Now this is where we actually call the unitary operator. And we can consider this unitary operator as a bit of a black box. So we don't actually know what the details are over here because we're dealing with a general phase estimation procedure. And this is the part of phase estimation that we need to adapt to a specific problem. And later in the video, we're going to see how to adapt this part of the procedure to the problem of order finding. So let's write down step 3. Step 3 involves this controlled unitary operation. So we have step 3 begins with the superposition. So we still have this superposition. So let's write the normalization coefficient of 2 to the minus m on 2 times the sum going from k equals 0 up to 2 to the power of m minus 1. And then we have the ket k followed by u to the power of k applied to its eigenstate. That's ket lambda sub s. So what is the effect of this unitary operator on this eigenstate? Every time we apply u, we're going to get an eigenvalue. And if we apply it k times, we're going to get k copies of this eigenvalue. So that's the same as raising this eigenvalue to the power of k. But we can use exponential laws, and we can bring that power inside, and we can multiply phi sub s by k. So let's write that out. We still have this superposition, so that's 2 to the minus m on 2, sum over k going from 0 up to 2 to the m minus 1. And then let's consider all of those factors that we get when we smush all the eigenvalues together. That's going to give us e to the 2 pi I k phi sub s. And then we're going to have ket k followed by ket lambda sub s. So we still have a superposition, but the result of this controlled unitary has given us these phase factors. And these phase factors depend on phi sub s. And now that we have this format, we can actually extract information about phi sub s by performing the inverse quantum Fourier transform. So that is step 4. Step 4 involves applying the m qubit inverse quantum Fourier transform to the top register. So that's this register over here with m qubits. And this notation has a joint sign over here. We have a dagger. That's telling us we're dealing with the inverse quantum Fourier transform. And this subscript over here is telling us that the dimension of the Hilbert space for this quantum Fourier transform is 2 to the m. So now that we have this quantum Fourier transform over here, let's see the effect of applying this inverse quantum Fourier transform. It's going to give us ket phi sub s with a little tilde. I'll put a tilde because this is an approximation. And then we're going to have ket lambda sub s. So this is the state of the top register, and this is the state of the bottom register. We're using that convention. So first we have this one on the left, and then this one on the right. And what have we got over here? If we measure the state of the top register, we're going to get phi sub s tilde. And that is a very good approximation for this phase factor. And that is the goal of this procedure. So once we perform this measurement, we have completed the procedure. We get a very good estimator for phi sub s. So this is all of the steps in the general phase estimation procedure. First, we have initialization, then we create a superposition, then we apply this black box procedure that is specific to every particular problem we're trying to solve with phase estimation. Then we apply the inverse quantum Fourier transform just to this top register of qubits. And then finally, we measure the top register. So that is what this symbol is telling us. We perform a measurement. And when we measure this top register, we're going to get this value, which is a really good estimator for phi sub s. And if we want to increase the precision, well, we're going to have to change the number of qubits in the top register. So we have some freedom to choose what m is, depending on how precise we want this estimate of phi sub s to be. Now that we have seen an overview of the phase estimation procedure, let's move on to the problem of order finding. And this is order finding in the context of Shor's factoring algorithm. So consider a positive integer, capital N. This positive integer is the number we're trying to factor using Shor's factoring algorithm. And we can express this number in binary. So we can express it as a string of bits. And those bits are going to start off at n sub 1. And we're going to go dot, dot, dot all the way to n sub L. So this is an L bit number. That is what it means to say that we have an L bit number. It takes L bits to represent n in binary. We can write this in summation notation. So we can write this as the sum over some index j going from 1 up to L of n sub j times 2 to the L minus j. So let's consider the case where j equals 1. That's n1. We have 2 to the L minus 1. So this bit over here is getting multiplied by 2 to the L minus 1. That's the power of 2 we're dealing with. And then if we go all the way to the smallest bit, that's going to give us j equals L. So for the j equals L term, we have n sub L, and that's 2 to the L minus L. L minus L is 0, so we have 2 to the 0, which is 1. So this is the ones bit over here. So now we can represent this number n in binary. Now it's important to start off with this definition so that we can move on and construct this quantum circuit diagram. The next thing that we need to define is an integer a. So a is a positive integer which lies between 1 and n. So n, for practical applications of Shor's factoring algorithm, is going to be a really huge semi-prime number. And the goal is going to be to factorize it into those two prime factors. So there's these two really big prime numbers that are being multiplied together to give a semi-prime number. And we also want to consider the case where those prime numbers are distinct. So we have a semi-prime number with two distinct prime factors. And those prime numbers are going to be very large as well. So this is a very difficult factoring problem. That's why we're trying to perform this factorization procedure with the help of a quantum computer. So considering this value of a, we also want a to satisfy the condition where the greatest common divisor of a with n is equal to 1. In other words, a and n are co-prime. So this is the kind of a we're looking for. And now, given this scenario, what we want is to find the minimum positive integer r. So we can write it like this. We have r greater than 0. It's a positive integer such that a to the power of r is equal to 1 mod n. So we're dealing with modular arithmetic over here. So r is called the order. R is the order of a mod n. So that is the language that we use. We're using the language of group theory. So we have the order of an element. And what we're trying to do is find the minimum positive integer r. It's very important that we specify that this is the minimum. Another way we could say this is it is the least positive integer r such that a to the r is equal to 1 mod n. That is the definition of the order. We're looking for the order r of a mod n. This is the statement of the problem. So we have two inputs. We have this value of a and we have this value of n. And the output to this procedure is going to be r. So we're looking for r. Let's have a look at the steps in this procedure. So this is based on the phase estimation procedure, but it's adapted to suit this specific problem. So let's have a look at step 1. Step 1 is just like up here, it is initialization. We're going to begin by initializing the two registers. And we're dealing with an m qubit register and an l qubit register. So this L is the number of bits that we need to express n in binary. So this is the binary representation. And have a look at what we're initializing this bottom register in. We're not initializing it in a single eigenstate. we're initializing it in the state 1. And later we will see that this is actually a superposition of eigenstates in disguise. We'll see that later as we go and progress through this quantum circuit diagram. So initialization begins when we initialize the m qubit register in the state 0 and the L qubit register in the state 1. Now these are not computational basis states for a single qubit. So this is not 0 and 1 for a single qubit. This is the state of an entire register. So alternatively, you could write this 0 as a string of m zeros. And this 1 can be written as a string of L minus 1 zeros followed by a final 1. So if you look at this binary representation, only n sub L would be equal to 1. And all of the other bits in this string would be equal to 0. So we just have L minus 1 of these zeros followed by a single 1. That is how you express 1 in binary. But n is actually much larger than 1. So we're dealing with a huge number in practical applications of Shor's factoring problem. So now we've cleared up this notation over here, and we know that this is shorthand notation for a register of m qubits and a register of L qubits. We've completed the step of initialization. Now let's create a superposition. That's the same step that we had up here. And what is this step going to involve? It's going to involve applying the Hadamard gate to all of the m qubits in the top register. And that's going to produce 2 to the minus m on 2 times the sum from k equals 0 up to 2 to the m minus 1 of ket k followed by 1. Now, we need to do some more definitions. We need to define a unitary operator before we can move on to step 3. So we have initialized, we've created a superposition, now we have to implement that controlled unitary. So let's define this unitary. So we need U to act on a ket labeled by B. So B is going to be whatever the state of this bottom register is. So B for bottom, it is the bottom register. And when U acts on B, it's going to be the same as multiplying by A, mod n. So this is the definition of this unitary operator. And now consider the case when B is equal to 1. So if we apply U, and we're also going to consider the case where we applied k times to the case where B is equal to 1. So we have 1 over here. That means we're going to have 1 over here, and we're going to apply this operator k times, which is going to give us a to the k mod n. So these are labels for the kets, and these kets are Dirac notation for quantum states. And you can see that if you apply the unitary operator once over here, it's going to take 1 to a. And if we apply it twice, it's going to take a to a squared, and then a squared to a cubed. And it's going to keep going up until we reach a to the k. And every time we do this, we are considering modulo n. We're working with modular arithmetic. Now we're ready to move on to the next stage, which is step 3. So step 3 is going to be very important because we're preparing a state that in the end, we're going to apply this inverse quantum Fourier transform to. But what is this state? So the state, which I'll write down here, is going to be 2 to the minus m on 2 times the sum going from k equals 0 up to 2 to the m minus 1. And then we're going to have ket k followed by the state that we get from applying u k times. So that is a to the k mod n. And let's elaborate on this state over here. A to the k mod n can be expressed as a superposition. We're going to have a normalization coefficient of r to the minus 1/2. Then we're going to have the sum over an index s going from 0 to r minus 1 of e to the 2 pi I times k s on r. And then we're going to have the eigenstates lambda sub s. So this state can be expressed as a superposition of the eigenstates of the unitary operator u. And now that we have this relationship, let's substitute this over here. So it would be nice if this was exactly equal to, but we're going to assume that it is approximately equal to. So it's a really good approximation. And then we're going to get r to the minus 1/2 times 2 to the minus m on 2. That's our normalization coefficient out the front. And then we're going to have two sums. We're going to have a sum over s going from 0 up to r minus 1. And then we're going to have a sum of k going from 0 up to 2 to the m minus 1. And then we're going to have e to the 2 pi I k s on r. And we're still going to have k as the label for these states in the first register. So that's ket k. And then we're going to have the label for this over here. We have lambda sub s. So that's these eigenstates. And now in this format, we can apply the inverse quantum Fourier transform to the m qubits in the top register. And when we do that, that will be step 4. When we do that, we're going to get another superposition. We're going to get the superposition r to the minus 1/2 sum from s equals 0 up to r minus 1 of a very good estimator for the quantity s on r. So we'll put a tilde over here. It's an estimator. And then we're going to have lambda sub s. So when we measure the first register, we're going to get an estimator for s on r. And that's going to be for one of these values of s. And that quantity that we get, s on r, is very important because this s on r, or estimator for s on r, so I'm putting a tilde on top, it is actually playing the role of phi sub s. So if we look at phi sub s over here, that is what we're dealing with. We're dealing with a specific application where phi sub s is equal to this quantity. And then we can actually take this quantity, and on a classical computer, we can apply the continued fractions algorithm. And that is how we're going to extract r. So that is the procedure that we're going to use. So you can see all of the steps in this order finding algorithm. We have initialization, we create a superposition, and then step 3 over here, we apply this controlled unitary, given this definition of u, and then we can manipulate that and put it in this format, and this is an approximation. And in this format, when we apply the inverse quantum Fourier transform to the m qubit register at the top, we get this state. And then when we measure this top register of m qubits, we're going to get the quantity s on r tilde. And that is a very good estimator for the quantity s on r. And it is from this quantity that we can extract r. So this part over here is the continued fractions algorithm, and that is done on a classical computer. But this part over here, this can be efficiently done on an ideal quantum computer. Now, we have used this relationship to go from this step to this approximation. Let's elaborate on this relationship. Let's consider a special case. So consider the case where k is equal to 0. Then we're going to have a to the 0, which is equal to 1. So the state 1 is actually equal to r to the minus 1/2, the sum from s equals 0 up to r minus 1. And this coefficient over here, we're going to have k equal to 0, so this is just going to be equal to 1. And then we're going to have lambda sub s. And so now we have a superposition of all of these eigenstates of u. And these eigenstates in this superposition are equivalent to 1. And why is this special? This is a very special relationship because it allows us to initialize the L qubit register in a superposition of eigenstates of the unitary operator u without any knowledge of r. So we don't know what r is when we initialize the states. R is a quantity we're going to find out. We're going to extract this integer at the end of this procedure. So there's no way that we can have knowledge of r when we're initializing this state. But this equation allows us to initialize the superposition of eigenstates without any knowledge of r. All we have to do is initialize in the state labeled by 1. And that is why this relationship is very important. So we still have this format, but instead of dealing with a single eigenstate, we're dealing with a sum of these eigenstates. So it is a superposition or a linear combination. And this r to the minus 1/2, that is a normalization coefficient out the front. Now, let's write this eigenstate in terms of these states, a to the k mod n. So it's a very similar expression. We can write that as lambda sub s is equal to r to the minus 1/2, so it's still the same normalization coefficient, and then we're going to have the sum over the index k going from 0 up to r minus 1. So we're not using s now, we're using k. And then we're going to put a minus sign. Over here we're going to have minus 2 pi I k s on r. And then we're going to have the states a to the k mod n. And the reason I'm writing it in this format is so we can verify that this indeed is an eigenstate of this unitary operator. So we have the definition of the unitary operator. This is how it acts on states. And we're going to verify that this format of an eigenstate is indeed an eigenstate. Let's have a look at some notable differences, between these two equations. In this equation, k is a fixed quantity, and s is the index which we are summing over. In this equation, s is a fixed quantity, and k is the index in which we are summing over. Another notable difference is that here we have a plus sign, and here we have a minus sign. Now, let's see the action of u on the eigenstate lambda sub s. So what is this action? Well, u, when it has a look at this normalization coefficient, is going to ignore it. So we're still going to have r to the minus 1/2. And u is also going to ignore this summation. So we're still going to have the sum of k going from 0 up to r minus 1. And it's also going to ignore these coefficients. So e to the minus 2 pi I k s on r. And when u reaches this stage over here, it's going to act on this state. And it's going to take whatever is inside this state, and it's going to multiply it by another factor of a, and then it's going to apply this mod n procedure. So that is going to give us an extra factor of a, and we can write that as a to the k plus 1. So that's just multiplying by a again, and then we have to apply this modular operation. We have mod n. So now that we have this format, let's change this k to another index. We can call that index j. So then we're going to have r to the minus 1/2, the sum over j going from 1 up to r, e to the minus 2 pi I. Then we're going to have j minus 1, and then we're going to have s on r. And we're going to have a to the j mod n as the label for this state. And what is this equivalent to? Well, if we look at this transformation, what have we done? We still have the same sum, it's just over a different index. So k is equal to j minus 1. Or in other words, j is equal to k plus 1. And when j is equal to 1, k is equal to 0. When j is equal to r, k is equal to r minus 1. So that is how these indices are related. Observe that we can use exponential laws to break this up into two exponential factors. This minus 1 and this minus sign are going to cancel, and we're going to have e to the 2 pi I times s on r. This is our eigenvalue. And the remaining terms are going to give us lambda sub s. Let's see why this is true. So now that we've gotten rid of this minus 1 over here by factoring out this factor, we can see that we have all the terms going from j equals 1 up to j equals r minus 1. And then we have an extra term of j equals r. So over here we have all the terms of k equals 1 up to r minus 1. But we have an extra term of k equals 0. And in fact, the k equals 0 term is equivalent to the j equals r term. Let's see why. When we set j equal to r, we're going to cancel with this r, so we're just going to be left with s times minus 2 pi I. So that's an integer multiple of 2 pi in the complex exponential. That's just going to evaluate to 1. So this coefficient is going to be equal to 1. And what about over here? If we have a to the power of r, that's equal to 1 by definition. That's the order. We're dealing with the order. So a to the r is equal to 1. we're going to have 1 over here, and 1 is the coefficient. What about the k equals 0 term? When we put 0 up here, this evaluates to 1, and when we have a to the 0, this also evaluates to 1. So the k equals 0 term in this sum is equivalent to the j equals r term in this sum. And all the other terms, going from 1 up to r minus 1, they are the same. So that means that this sum and this sum are equivalent up to a factor of e to the 2 pi I s on r. So this quantity over here is the eigenvalue. So it's just like this equation up here. So we can make a link. We can link these quantities together, and we can identify that phi sub s in the context of this order finding algorithm is equal to s over r. And when we apply phase estimation to this unitary operator, what we're actually doing is we're actually finding a really good estimate for the quantity of s on r. And the precision of that estimate depends on the value of m we choose. So that's the number of qubits in the top register. And then once we have gotten this value, we can apply the continued fractions algorithm on a classical computer, and that's going to be used to extract the value of r. And once we have r, we have done this task of finding the order of a mod n. So we've taken those inputs of n and a, and the single output of this procedure is the positive integer r. So that is the quantum order finding subroutine of Shor's factoring algorithm. We're going to see examples of this procedure. And we're actually going to see how to implement this procedure over here. That's step 3. And this procedure has a special name. It's called modular exponentiation. That is how we're going to implement step 3. And we'll see that in the next few videos.